Good evening, all. I welcome you all to the week's 6 live interactive session for the course Chemical Reaction Engineering 2. Now, let's get started with the uh, session. So, as usual, we will have a brief recap of the lectures of week 7. Uh, Week 7 again had 5 lectures starting from lecture 31 to lecture 35. Uh, where lecture 31 and 32 covered the overall effectiveness factor. So, in lecture 31, the case where both the external and internal mass transfer resistance are comparable uh, in the catalytic reaction was discussed, where steady state molar balances were derivation was initiated. Here again, there was a discussion on how the area varies widely. For example, for the case of an external surface area to the internal surface area, where the internal surface area within the catalytic pellet is much larger compared to that of the external surface area was shown with an example in case of a silica and alumina catalyst, and then the steady state molar balances was initiated in the lecture 32. The rate of reaction and the overall effectiveness factor was discussed, where the definition for overall effectiveness factor was also introduced. And then the the lecture also had a, you know uh, the formula was derived for the internal effectiveness, the overall effectiveness factor. And lecture 33 had a discussion on identification of internal diffusion and the reaction limited regimes. Here, Weiss-Prater criterion was discussed, and an example problem was solved where two different sizes of catalyst pellet and the observed reaction rate uh, uh, was given, from which it was the Weiss-Prater criterion was calculated, and uh, it was discussed. There was discussion on the internal diffusion resistance dominated regime. And then lecture 34 was on packed bed reactor design. Initially, the Mears criterion, one on concentration based and the other on the temperature based, was discussed. This was followed by packed bed reactor design, where the expression for the conversion was uh, derived. And the final lecture 35, uh, was on generalized criterion for diffusion and reaction limited conditions. So in this lecture, the limitation of the Weiss-Prater criterion was discussed, uh, and a need for a generalized framework was explained based on the example of conversion of CO2 to carbon monoxide reaction, where the Weiss-Prater criterion failed to indicate that the reaction is actually limited by the internal diffusion. And then the generalized criterion was brought into picture, and the the criterion based on the criterion, it was identified for the reaction that the reaction also had a internal diffusion limited regime. and almost all the derivations were based on the first order reaction, which can be extended to other orders as well. That was discussed during the the week's lecture. Now let's get on to the practice assignment of week 6. Question number 1. If minus RE prime rho B into R into N by KCCAB is less than 0.15, then it indicates that whether it is option A, external mass transfer limitation exists, or is it option B, no internal mass transfer limitation exists, or is it option C, internal mass transfer limitation exists, or is it option D, no external mass transfer limitation exists. So which of these is the right option when the given parameter is less than 0.15? So if we look into the given expression, we can find out that this is nothing but your Mears parameter, and if the Mears parameter is the Mears parameter based on concentration, and if Mears parameter based on concentration is less than 0.15, then it indicates that there is no external mass transfer limitation. Now question number 2. Weiss-Prater criteria can predict the internal mass transfer limitations for which of these following options? Whether it is A for nth order reactions, or is it B LH mechanism reactions, or is it Lee-Riddle mechanism reactions, or for all of the above, the Weiss-Prater criteria can predict the internal mass transfer limitation. Which of the following is right? So the answer is it can predict the internal mass transfer limitation only for the nth order reaction. So this is what was the main point of the lecture 35, where there was a limitation for the Weiss-Prater criteria and a need for a generalized framework for identifying the internal mass transfer limitations, where the reaction of carbon dioxide getting converted to carbon monoxide was discussed, where this reaction was actually limited by the adsorption of the product on the catalyst surface, which was inhibiting the reaction. The Weiss-Prater criteria fails to predict the internal mass transfer limitations when the reaction mechanism is not of nth order, whereas if it is of some adsorption based, like LH mechanism, Langmuir-Hinshelwood kinetics based, or it is Lee-Riddle mechanism based, or it is for an exothermic reaction, or it is having some kind of an inhibition. So it is the solution for this question is it can predict only for nth order reaction only. Now let us go on to question number 3. Weiss-Prater parameter is the ratio of is it the ratio of observed reaction rate to the reaction rate evaluated at concentration at the surface of the pellet, or is it the observed reaction rate to the diffusion rate, or is it rate evaluated at the surface of the pellet at the conditions of pellet surface condition to the diffusion rate, or is it option D, observed reaction rate to the rate evaluated at the bulk conditions? So which of the following following is correct? So the answer for this question is Weiss-Prater parameter is mainly for the internal identifying the internal diffusion limitation. So obviously it cannot be option D, that is observed reaction rate to the rate evaluated at the bulk condition, right? So which of the other three would be the right option? So obviously it is the observed reaction rate to the diffusion rate, because it has to say the internal diffusion limitation. So obviously it should have a component either in the numerator or in the denominator, a diffusion rate component. So it is the observed reaction rate to the diffusion rate. So the Weiss parameter is given by CWP is equal to eta into phi 1 square. So where your eta is your internal effectiveness factor and phi 1 square is nothing but your square of your Thiele modulus. And your eta, that is your internal effectiveness factor, is given by the ratio of observed or actual reaction rate to the reaction rate evaluated at CAS, and your Thiele modulus is given by reaction rate evaluated at the surface at CAS to the diffusion rate. So uh, the denominator in the second term, sorry, in the first term, and the numerator in the second term gets cancelled. So you will get your Weiss parameter to be equal to actual reaction rate to the diffusion rate. So the next question, Mears criterion where there will be no temperature gradient is which of these following? So Mears criterion, there are two Mears criterion as we as it was discussed in the lecture and we just saw in the recap also. One is concentration based and the other one is the temperature based. So uh, and also we just saw that it is based on the uh, it dictates whether it determines whether it is a external diffusion controlled reaction or not. So, uh, now let's see what are the options. So, option A is given by modulus of uh, a heat of reaction into reaction rate into bulk density into the radius of the pellet into E, which is nothing but your activation energy by heat transfer coefficient into square of temperature into your universal gas constant. So whether this term is greater than 1 or it should be less than 1 or it should be less than 0.15 or it should it be greater than 0.15 for no temperature gradient existing. That is, everything is at the bulk bulk temperature. The conditions inside the pellet, the condition outside the pellet, everywhere the temperature is at the bulk temperature condition. So when does this happen? So the option, the correct answer is, it is option C. So the Mears criterion with respect to temperature should be less than again 0.15. So for both concentration based and the temperature based, the Mears criterion should be less than 0.15 so that the external diffusion, whether it is the external concentration gradient or the external temperature gradient, there is no change in that to the internal conditions as well. Okay. Now let's go on to the question number 5. Question number 5. Nitric oxide plays an important role in smog formation and there are great incentives for reducing its concentration in the atmosphere. It is proposed to reduce the concentration of nitric oxide in an effluent stream from a plant by passing it through a packed bed of spherical, porous, carbonaceous solid pellets. A 2% nitric oxide and 98% air mixture flows at the rate of 1 into 10 power minus 6 meter cube per second, that is 0.001 decimeter cube per second, through a 2-inch internal diameter tube packed with porous solid pellets at a temperature of 1173 Kelvin and a pressure of 101.3 kilopascal. The reaction is given by NO plus C gives CO plus half N2. It is first order with respect to nitric oxide, that is minus R prime NO is equal to K1 double prime SA into concentration of nitric oxide. And it occurs primarily in the pores inside the pellet, where the internal surface area is given by 530 meter square per gram, and your um, intrinsic reaction rate constant K1 double prime is given by 4.42 into 10 power minus 10 meter cube per meter square second. This is with respect to the surface uh, surface surface. So additional information given are at 1173 Kelvin, the fluid properties are, so the kinematic viscosity nu is given by 1.53 into 10 power minus 8 meter square per second. Your effective diffusivity dE is given by 1.82 into 10 power minus 8 meter square per second, and your gas diffusivity DAB is given by 2 into 10 power minus 8 meter square per second. And the properties of the catalyst and the bed are rho C, which is the density of the catalyst particle. It is equal to 2.8 gram per centimeter cube, which is nothing but equal to 2.8 into 10 power 6 gram per meter cube. The bed porosity is given by phi, which is equal to zero point 0.5. And your bulk density of the bed is given by rho B. Rho B is equal to rho C into 1 minus 5. So, which gives rho C is nothing but 2.8 into 10 power 6 gram per meter cube into 1 minus 5. 5 is 0.5. So, you will have 2.8 into 10 power 6 into 1 minus 0.5, which is nothing but equal to 0.5. So, 2.8 into 0.5 into 10 power minus 6, you will end up with 1.4 into 10 power 6 gram per meter cube. The bulk density of the bed is 1.4 into 10 power 6 gram per meter cube. And the radius of the pellet is given as 3 into 10 power minus 3 meter, which is nothing but 3 millimeter. And the sphericity is 1. That means it is a spherical. So they have given a spherical catalyst. It is also given in the text. Spherical porous carbonaceous solid pellet. So the sphericity is nothing but 1. Now we can also convert this specific reaction rate constant in terms of per gram of the catalyst, per gram of catalyst, and also per considering the volume of the reactor also. So with respect to per gram of catalyst, so K1 prime is K1 double prime into SA, which is there. SA is nothing but your internal surface area. So, which is equal to your K1 double prime is 4.42 into 10 power minus 10 meter cube per meter square second into internal surface area is given by 530 meter square per gram. So, you will end up with multiplying these two, you will end up with K1 prime is equal to 2.34 into 10 power minus 7 meter cube per gram second. Also, we know the bulk density of the catalyst bed. So, which is nothing but 1.4 into 10 power 6 gram per meter cube. So, we can also convert it with respect to the in the specific reaction rate in terms of the uh, considering the reactor volume also. So, K1 is equal to K1 prime into rho B. So, K1 prime we already calculated. It is nothing but 2.34 into 10 power minus 7 meter cube per gram of catalyst per second, multiplied by your bulk density of the catalyst is 1.4 into 10 power 6 gram per meter cube. So, multiplying these two, you will get K1 is equal to 0.328 second inverse. Now, what are we supposed to calculate? We have to calculate the Weiss-Prater parameter, CWP, and then we have to check whether it is internal mass transfer limiting. And part 2 of the question is calculate the Mears parameter MR for external diffusion limited, and we have to check whether it is external mass transfer limiting reaction. And part 3 of the question is calculate the weight of solid porous catalyst necessary to reduce the nitric oxide concentration of 0.004%, which is the Environmental Protection Agency's limit. So, there is a packed bed reactor where porous catalyst, spherical catalyst containing carbon particles is packed in the reactor, and nitric oxide with 2% concentration enters the reactor, and nitric oxide with 0.004% concentration comes out of the reactor, the final concentration. So we have to check. So initially, whatever in the bulk, the concentration of the nitric acid is given by CAB, and if there is an external mass transfer resistance, then it will reach the surface with a concentration of CAS, and if there is a internal mass transfer resistance, then the concentration of the nitric oxide within the pellet will be Ca. Here where the porous catalyst is spherical in shape. Now let's start solving this problem. So initial concentration of nitric oxide CaB naught is 2%. In the bulk, this is the bulk concentration, that is what is given. So because this enters the reactor, and 2% enters the reactor and 0.004% comes out of the reactor, and the actual measurable parameter in reality will be this bulk concentration only. So the initial concentration of nitric oxide is CaB naught is equal to 2%, and final concentration of nitric oxide CaB is 0.004%. Now we can calculate the conversion. Okay, so we have to convert this percentage into the values, the mole fraction. So divided by 100, but again in numerator and denominator it will be 100. That is why we have taken 2 and 0.004 directly. Okay, so conversion is given by CaB naught minus CaB by CaB naught. So initial minus final by initial, that is the conversion concentrations. So 2 minus 0.004 by 2. So it is actually 2 by 100 minus 0.004 by 100 divided by 2 by 100. The 100 gets cancelled everywhere. So you will get into this, and you will end up with the conversion value to be 0.998, which is 99.8% conversion as it comes out of the reactor. Okay. Now step number 1 is, what is the first question asked? It's been asked to first of all calculate the Weiss-Prater parameter and then find out if it is internal diffusion limiting. So Weiss-Prater parameter is given by CWP is equal to eta into phi 1 square, where eta is your internal effectiveness factor and phi 1 square is your square of your Thiele modulus. Now we have also been given the information that the reaction is first order with respect to nitric oxide, where the reaction rate expression is also given in intrinsic reaction rate expression. So considering that, so your Weiss-Prater parameter becomes CWP is equal to eta into phi 1 square, which is nothing but equal to 3 into phi 1 into cot hyperbolic phi 1 minus 1. This is for the first order reaction, and they have given the reaction to be first order. Now in this expression, we have to know, in order to find out the Weiss-Prater parameter, we have to know what is the Thiele modulus and also what is the internal effectiveness factor. So Thiele modulus for the first order reaction is given by phi 1 is equal to R into square root of K1 double prime into SA into rho C by dE, where SA is your internal surface area available within the catalyst, and then catalyst particle, and then rho C is your density of the catalyst particle, right? So this internal effectiveness, your Thiele modulus you calculate for the individual catalyst particle, right? So we have already been given what are the values of each of the parameters. We know that radius of the catalyst particle is 3 into 10 power minus 3 meters, and then K1 double prime is 4.42 into 10 power minus 10, and your surface area of the catalyst particle is 530, and your density of the catalyst particle is 2.8 into 10 power 6. and your effective diffusivity is 1.82 into 10 power minus 8. We should also have a look into the units so that there is a unit consistency. Otherwise, it may lead to wrong results. So here all the units are considered and it matches. So substituting all the values, you will get your Thiele modulus to be 18. Now, now let us look into the formula for the uh, Weiss-Prater parameter. So Weiss-Prater parameter is given by eta into phi 1 square, which is equal to 3 into phi 1 cot hyperbolic phi 1 minus 1 in the case of first order reaction. Now, should we really substitute into this formula, or we can directly find out the value of your eta, which is your internal effectiveness factor. So, if we look into the Thiele modulus value, you will find out Thiele modulus value is 18, which is very much great, which is very high, right? That means your very high Thiele modulus, then your internal effectiveness factor can be taken as 3 by phi 1. So, 3 by phi 1 is nothing but 3 by 18, which is equal to 0.167. Now, so now substituting the value of your internal effectiveness factor and your Thiele modulus value. Now, let's find out what is the Weiss-Prater parameter. So, CWP is equal to eta into phi 1 square, that is equal to 3 by 18 into 18 square. So, which is nothing but 54, right? So, the Weiss-Prater parameter is says that if the Weiss-Prater criterion says that if CWP is less than 1, then there is no internal mass transfer limitation. However, if you see the value here, the value of the Weiss-Prater parameter is 54, which is very much greater than 1. That means there is an internal mass transfer limitation for this particular reaction. There exists an internal mass transfer limitation for this reaction. Now, let me say one more thing. Do we really need this value, or can we also find out in much earlier stage whether this reaction is having an internal mass transfer limitation? So, we know that, your Thiele modulus is 18, which means it is very high. That means your denominator of the Thiele modulus, that is your diffusivity, the denominator is very small compared to your numerator. That means your Thiele modulus formula also we know, which gives the rate of reaction at the surface catalyst surface condition to the diffusion rate. So, if the denominator of the Thiele modulus is very small and the value of Thiele modulus is very high, it automatically says that the reaction is internal diffusion delimited. So this is just this is an additional information I am just discussing, because we have earlier seen in the previous lectures and we have calculated also. So that means when Thiele modulus is very high, there is a internal diffusion limited. However, this Weiss-Prater parameter gives an additional confirmation of that its value is very much greater than 1. That means there is an internal mass transfer limitation for this reaction. Okay. Now, let's go on to the part 2 of the question. So, part 2 of the question is, we have to calculate the Mears parameter, that is Mears parameter based on the concentration, and we have to check whether it is external mass transfer limiting also, or it is not limited by the external mass transfer. Now, your Mears parameter is given by MR is equal to minus RA prime observed into rho B, where it is the bulk density of the bed, into R into N divided by Kc into CAB, where rho B is your bulk density of the bed and R is your radius of the pellet, and N is your order of the reaction, and Kc is nothing but your external mass transfer coefficient, and Cab is your bulk concentration. So this R observed can be rewritten as uh, overall effectiveness factor multiplied by the rate of reaction at the bulk condition, because the overall effectiveness factor is the ratio of the observed reaction rate to the reaction rate when all the parameters are at the bulk condition. Okay, so it is overall effectiveness factor multiplied by reaction rate at the bulk condition into rho b into r into n divided by kc into cab. Now further coming down, so we can express this uh, bulk reaction rate as K1 prime into CAB, right? And then one more thing is that it is a first order reaction. So substituting these two, you will get the Mears parameter is equal to overall effectiveness factor. So omega into K1 prime into CAB into rho B multiplied by R divided by Kc into CAB. Now again your CAB and CAB in the numerator and denominator gets cancelled, and you will end up with your Mears parameter as uh, overall effectiveness factor omega multiplied by K1 prime into rho B into R by Kc. Now, can we calculate the Mears parameter? So, what are the values we have and what are the values we have to first of all determine before actually calculating the Mears parameter? So, we have the value for K1 prime, right? Which we have already calculated and it is given in the question. And also the bulk density of the bed is also calculated and it is available. Radius of the pellet is available. However, we do not have the mass transfer coefficient Kc and your overall effectiveness factor. Now let us look into the overall effectiveness factor. So unknowns in the above equation are, in order to calculate the Mears parameter, are your overall effectiveness factor and your mass transfer coefficient. Now let us see what is overall effectiveness factor. So overall effectiveness factor is given by the internal effectiveness factor divided by 1 plus eta into K1 double prime SA into rho B by Kc into AC, right? So again, looking into the estimation or the formula of the overall effectiveness factor, the overall effectiveness factor also requires the value of your mass transfer coefficient. So the next parameter that is to be calculated is your mass transfer coefficient. Now let us see how to calculate the mass transfer coefficient. So estimation of mass transfer coefficient Kc. So in the last week's lecture, two methods for determination of the mass transfer coefficient was discussed. One was the Thienes-Kramer correlation and the other one was based on Kolben correlation. Now we are using Thienes-Kramer correlation. We can also use Kolben correlation. However, here we are trying to use the Thienes-Kramer correlation for determining the mass transfer coefficient Kc. So what is Thienes-Kramer correlation? Thienes-Kramer correlation is given by modified Sherwood number is equal to 1 into modified Reynolds number power 0.5 into Schmidt number power 1 by 3. Now let's start calculating. So here in order to find your mass transfer coefficient, first of all we have to find what is your Schmidt number, what is your Reynolds number, and then what is your modified Reynolds number, and what is your modified Sherwood number. So Schmidt number is given by nu by dAB, which is nothing but momentum diffusivity to mass diffusivity, or it's a ratio of kinematic viscosity to your mass diffusivity. So it's nu by dAB. So nu is given as 1.53 into 10 power minus 8 meter square per second, the fluid conditions, fluid parameters, and your dAB, the gas diffusivity, is given by 2 into 10 power minus 8 meter square per second. So substituting these two, you will get your Schmidt number is equal to 1.53 into 10 power minus 8 divided by 2 into 10 power minus 8, which is nothing but equal to 0.765. So now, as of now, we have determined what is the Schmidt number. The next parameter to be determined is your modified Reynolds number. So your modified Reynolds number is given by your Re prime is equal to Re divided by 1 minus phi into gamma. Where your phi is your bed porosity. So do we have the bed porosity value? Yes, it is given as 0.5. And your gamma, which is nothing but your sphericity or shape factor. Here they have already given it is a spherical pellet. So that means your shape factor is going to be 1. Now what is your Reynolds number? Your Reynolds number is given by u into dp by nu, where u is your superficial velocity, dp is your particle diameter, and nu is your kinematic viscosity. Okay, so now what are the parameters we already have in the case of for determining the Reynolds number? We already have the diameter of the particle. So the radius of the particle is given as 3 into 10 power minus 3 meter. So diameter will be 6 into 10 power minus 3 meter. And your kinematic viscosity nu is given by 1.53 into 10 power minus 8 meter square per second. Right. Now, how to determine your, we do not have the value for your superficial velocity. So how to determine your superficial velocity? So superficial velocity can be determined if we have the volumetric flow rate value and area of cross section of the reactor, right? So your volumetric flow rate, have they given the volumetric flow rate in the question? Yes, they have given the volumetric flow rate. If you look into the question, they have given the mixture flows at a rate of 1 into 10 power minus 6 meter cube per second. That is nothing but 0.001 decimeter cube per second. So your V naught is nothing but 1 into 10 power minus 6 meter cube per second. Right? Now, so V naught is 1 into 10 power minus 6 meter cube per second. And then next is your area of cross section of the, sorry, it's not the bed, it's the entire reactor. Okay, let's change that. Reactor or the tube, whatever they have given. Okay. So your area of cross section is this. This is your area of cross section. That means it is a circular cross section. Right. So your area of cross section is nothing but pi d square by 4. So what is the value of your the diameter of the tube? They have given the diameter of the pipe or tube or the reactor is 2 inch. That means 2 into 2.54 into 10 power minus 2 meter, that is 5.08 into 10 power minus 2 meter is your diameter of the pipe. Now, substituting the value of diameter of the pipe, you will get, so AC, your area of cross section of the reactor AC is equal to pi into 5.08 into 10 power minus 2 the whole square divided by 4. You will end up with a value of 2.03 into 10 power minus 3 meter cube. Sorry, meter square. Right? Now, what will be the superficial velocity? Your superficial velocity U is given by your volumetric flow rate by area of cross section. Alright? So, 1 into 10 power minus 6 divided by 2.03 into 10 power minus 3. You will end up with the value of superficial velocity to be 4.93 into 10 power minus 4 meter per second. Right? Now, next, how we have to calculate the Reynolds number. We have the superficial velocity value. We have the diameter of the pellet. We also have the kinematic viscosity value. So substituting those values, you will get, so Reynolds number is equal to 4.93 into 10 power minus 4 into 6 into 10 power minus 3 divided by 1.53 into 10 power minus 8. So you will get Reynolds number is equal to 193.3 in this case. Now the modified Reynolds number is given by Re prime is equal to Re by 1 minus phi into gamma. So the porosity of the bed phi is equal to 0.5. So one more thing is that here phi denotes your porosity of the bed, whereas your phi 1 denotes your Thiele modulus. Okay. So we shouldn't get, since both have same notation as phi, we shouldn't get confused, and that is why it's described as phi for porosity of the bed, whereas when we discuss the Thiele modulus, we showed it as phi 1, right? So phi 1, it is denoted as, Thiele modulus is denoted as phi 1, whereas porosity of the bed is denoted as phi. Okay. So, and your sphericity or shape factor is equal to 1, since it is a spherical catalyst particle. Right. So, the modified Reynolds number is given by 193.3 divided by 1 minus 0.5 into 1, which is nothing but 386.7. Now we have to find out what is the modified Sherwood number. So modified Sherwood number is given by, this is nothing but your Theonis-Cramer correlation. So modified Sherwood number is equal to 1 into modified Reynolds number power 0.5 into Schmidt number power 1 by 3. So that is equal to 1 into 386.7 power 0.5 into 0.765 power 1 by 3, which is nothing but 17.985, which is equal to which is approximately equal to 18. So your modified Sherwood number is 18. Now we have to find out from the modified Sherwood number what is your mass transfer coefficient. So the relationship between the Sherwood number and the mass transfer coefficient, modified Sherwood number and the mass transfer coefficient is Kc, your mass transfer coefficient, is equal to modified Sherwood number into dAb by dP into 1 minus phi by phi into gamma, where your dAb is your gas diffusivity, right? And your dP is your diameter of the pellet, and phi is your bed porosity, and gamma is your shape factor or your sphericity. Now we have all the values. So substituting all the values, so Kc is equal to 18 into 2 into 10 power minus 8 divided by 16 to 10 power minus 3 multiplied by 1 minus 0.5 by 0.5 into 1. So you will end up with Kc is equal to 6 into 10 power minus 5 meter square per second, right? So now we have what is the mass transfer coefficient. Now what else we have to find for finding out the overall effectiveness factor? There was also a external area available per volume of the reactor AC. So AC is given by 6 into 1 minus 5 divided by dP. So that is equal to, we have all the terms. We have porosity of the bed. We also have the diameter of the particle. So we can find out what is the external area per unit volume of the reactor AC. That is equal to that is equal to 6 into 1 minus 0.5 divided by 6 into 10 power minus 3. So you will end up with the external area per unit volume of the reactor AC is equal to 500 meter square per meter cube, right? So we have the external mass, we have the external mass transfer coefficient value, which is Kc is equal to 6 into 10 power minus 5 meter square per second, and then your external surface area per unit volume of the reactor, which is equal to 500 meter square per meter cube. So now what is the overall effectiveness factor? So overall effectiveness factor omega is equal to internal effectiveness factor eta divided by 1 plus eta into K1 double prime into SA, where which is the internal surface area within the pellet, into bulk density of the catalyst divided by Kc, which is your mass transfer coefficient, into AC, which is nothing but your external surface area per unit volume. of the reactor. So we have all the values. So omega is equal to 0.167 divided by 1 plus 0.167 into K1 double prime is 4.42 into 10 power minus 10. Your SA is 530 and your rho B is 1.4 into 10 power 6 and Kc is 6 into 10 power minus 5 and AC is 500. So substituting these we'll get, so 0.167 divided by 1 by 0.167 divided by 1 plus 1.83. So you will end up with your uh, overall effectiveness factor to be 0.059. Now we have our, so for the Mears criterion, Mears parameter, the two unknowns were our mass transfer coefficient and our and the overall effectiveness factor. So we have calculated the values of these. Now we can calculate what is the Mears parameter, right? So Mears parameter is given by omega into k1 prime into rho b into r divided by kc. So substituting the values, we get your Mears parameter is 0.059 into 2, where k1 prime is 2.34 into 10 power minus 7 into rho b, your bulk density of the catalyst is here rho b is your bulk density of the catalyst bed, which accounts for the porosity of the catalyst. So which is nothing but equal to 1.4 into 10 power 6 and r is the radius of the catalyst particle, which is 3 into 10 power minus 3, and Kc we have calculated and found it to be 6 into 10 power minus 5. So substituting these values, we get our Mears parameter to be 0.97. We know that if Mears parameter is greater than 0.15, then there exists an external mass transfer limitation. So here in this case, we have our Mears parameter to be 0.97. So 0.97 is obviously greater than 0.15. That means there exists an external mass transfer limitation. So what are the two observations from the Weiss-Prater criterion and Mears criterion we observed? We observed in this system of a packed bed where this nitrous oxide is converted to nitrogen, uh, it involves both the external and internal mass transfer resistances limiting the reaction. That means the bulk concentration, the concentration on the surface of the catalyst is not same as the bulk concentration, because there is a resistance offered, an external mass transfer resistance offered, and similarly the concentration inside the pellet is not same as the concentration at the surface of the pellet. Again there will be a concentration gradient from outside surface of the catalyst to the inside of the catalyst. So we have to account for both these limitations and resistances while actually calculating the other parameters or for understanding this reaction mechanism. Okay. Now the next part of the question is calculate the weight of the solid porous catalyst necessary to reduce the nitric oxide concentration of 0.04, which is below the Environmental Protection Agency limit. So your initial concentration was 2% and your final concentration is 0.004%, and we have already calculated the conversion to be 0.998. So this is the conversion at the exit of the reactor, right? Because this is what is the concentration of nitric, this 0.004% is the concentration of the nitric acid coming out of the reactor. That means it is the conversion what we have obtained is the conversion at the exit of the reactor, right? Okay, so conversion of the exit, conversion at the exit of the reactor for a packed bed reactor can be expressed as x is equal to 1 minus exponential of minus omega k1 double prime SA into rho b into L by U, where your omega is your overall effectiveness factor and k1 double prime is the intrinsic specific reaction rate constant with respect to area, area available, and then SA is your internal surface area available, rho b is the bulk density of the catalyst bed, and L is the length of the reactor, right? And U is your superficial velocity. So this K1 double prime SA into rho b can be rewritten as K1, right? So rewriting the expression, we get conversion is equal to 1 minus exponential of minus omega into K1 into L by U. Now, there L is the total length of the reactor. Now, rewriting this expression, minus omega K1 into L by U is equal to ln of 1 minus x. Why are we rewriting the expression? So, in this expression, we have the value of overall effectiveness factor, we have the value of the specific reaction rate constant, and then we have the value of superficial velocity, we have the value of conversion. Whereas, we have to find what is the length of the reactor, L, or length of the bed, right? Total length of the reactor or total length of the back bed. So, in order to find out that, we are rewriting the expression. So, rewriting the expression, we get the length of the reactor is equal to U by omega into K1 multiplied by ln of 1 by 1 minus x. So, substituting this, we get, we have all other values. So, substituting all the values, we get length of the reactor L is equal to, we have the value of U, that is your superficial velocity is 4.93 into 10 power minus 4 meter per second. Your overall effectiveness factor is omega is 0.059, and your specific reaction rate constant is 0.328 second inverse, and ln of 1 by 1 minus 0.998, where 0.998 is your conversion, right? So this will end up with your length of the reactor to be 0.16 meter. So now we have found out what is the length of the reactor. But what is the actual question asked? The actual question asked is, what is the weight of the solid porous catalyst required to have a conversion of 99.8 or to have a final concentration of nitric oxide as 0.004%. Now, so what should we find? The weight of the catalyst. Alright, so the weight of the catalyst required is equal to, W is equal to your bulk density of the catalyst bed into area of cross section of the reactor AC multiplied by length, because your density multiplied by volume gives your weight of the catalyst required. So, do we have all the required parameters? Yes, we have the bulk density of the catalyst bed, which is 1.4 into 10 power 6, right, gram per meter cube, and your area of cross section of the reactor is 2.03 into 10 power minus 3 meter square, and your length of the reactor is 0.16 meter. So, substituting all, you will get your weight of the catalyst as 455 grams. So, this is the weight of the catalyst. So, we can also, so this is one way of, determining the weight of the catalyst required for a particular conversion in a particular reactor. So, we can also, instead of, first finding out the length of the reactor and from there, multiplying the density and area of cross section, we can also rewrite the mass balance or the expression, right, of conversion in terms of the weight of the catalyst, and find out what is the and integrate that expression. That is, we can write it as dCAB by dW, which is nothing but your change in concentration with respect to weight of the catalyst, and rewrite the expression for the conversion, and then we can also, we can integrate that expression and find out what is the weight of the catalyst in the other format also, and from there again you can find out the length, because you have the formula W is equal to rho B into AC into L, right? So this is another way. So in this question, so we found out, so three things were asked. First one is to find out the Weis-Prater parameter, and the next is Mears parameter, and then the weight of the catalyst required for a particular exit concentration, right? And also it was it was asked to identify whether the reaction is having internal mass transfer resistance and external mass transfer resistance. And we found out that the conversion, mm, the reaction involving conversion of nitric oxide to nitrogen, it involves reaction that is limited by both external mass transfer resistance and internal mass transfer resistance. As your base parameter was much greater than 1, indicating that there is an internal mass transfer resistance offered, and similarly your Mears parameter was greater than 0.15, indicating that there is a external mass transfer resistance being offered for the reaction. And once we incorporate all the, once we identify the mass transfer coefficient, your overall effectiveness factor, your internal effectiveness factor, Thiele modulus and everything, and substituting in the expression for conversion, as we have already the data on the conversion because they have given the exit concentration also, and we can find out what is the catalyst required for quantity of catalyst required for that particular conversion, right? Because the concentrate, the way the quantity of catalyst required is very critical to achieve certain conversion. So we can find out what is that quantity required and what is the length of the bed that is required when we have the area of cross section of the reactor, right? Yeah, that's it with the session. Thank you. Thank you all. Hope this session would be would have helped you in getting some insights and help you in solving the assignment 7. Thank you all.